beginning. There we go. Hello again. Today's lecture actually turns out to be a pretty difficult one for a lot of students. It has a lot of material to cover, but it's extremely important. Our cells need to be turned on and off. When they're turned on, they do stuff. Muscle cells contract. Hormone-releasing cells will release more hormones. It's what they do. Every cell has a job to do. And to keep yourself in homeostasis, or to ramp up if you need to, like your heart has to beat faster during exercise, you have to turn stuff on, and then you have to turn it back off again. And knowing how this works is really critical, because most of your disease states involve in some way cells that are either working too much or too little. And so if you know how that happens, you can figure out what's going on with the disease. And many, if not most, of our medical treatments involve turning some cells on more or less so that you can balance it back out and make it the way it's supposed to be. So membrane activation, activating these cells, happens in two real basic ways. One is with nerves, and the other is with hormones. Hormones are molecules that flow through the blood and bind onto a cell and turn it on. Nerves are specialized cells that send a signaling molecule that then binds to the cell and turns it on. So we turn on cells with nerves using electric currents. It's not a binding of a hormone type thing. Instead, it's actually a flow of electricity across the membrane that causes it to turn on and off. That's why you can put an EKG electrode on and you can see how the electricity is actually flowing through the heart muscle, and you can tell what's going on in the heart. So we have certain cells that turn on this way. They're primarily nerves and muscle cells. Those are called excitable cells. They're excitable by you open it and let electricity flow across. And so we have nerves turning on electrically stimulated cells, and then those electrically stimulated cells are either other nerves or muscle cells. And then we can also turn them on with hormones. Today we're doing nerves. Next lecture is hormones, and then we'll know how to turn cells on and off. Okay, if you have current flowing through your house and coming out your outlet, those are electrons. They flow through a wire, and they are so tiny that the body has no way to control their flow. So we don't use electrons to flow currents. We use ions. Ions are molecules that are, way, way, way bigger than electrons. And they either have one too many or one too few electrons, and therefore they have a charge. They have basically as much power as one electron, except they're big enough that we can open a gate and they go through, close a gate and they stop. A cation is a positively charged electron. We have cats. I'm very positive about cats. So cations, positive ions. Anions are the negatively charged ions. And that matters because if you're trying to turn on a cell, generally you make it more positive. If you want to turn it off, you generally make it more negative. Our electrolytes, or ions, are sodium, potassium, and calcium. There are some others that jump in and help out at times, but for this purpose, sodium, potassium, and calcium are our electrolytes, and they're called that because they have electrical charges, and therefore they can be used to cause electrical currents. Sodium and calcium are extracellular. Those are kept outside the cell. And potassium is your intracellular ion. These are all positive ions. So these guys are on the outside. Potassium is on the inside. And they are kept there by the sodium-potassium pumps that keep pumping sodium out and potassium in whenever it leaks the wrong way, or you stimulate a cell and it goes onto the side it's not supposed to be on. Those sodium-potassium ATPase pumps we talked about previously keep working 24/7 and keeping plenty of sodium outside, plenty of potassium inside, so you can use it to make ion flow and electrical flow. So here we have a cell, and here we have a bunch of sodium on the outside, and we have a bunch of potassium on the inside. Some sodium's leaking in, some potassium's leaking out. But your sodium-potassium pumps are chugging away, keeping the sodium out and the potassium in. So generally speaking, the sodium stays out here, the potassium stays in here, unless you want it to move. Now, the membrane potential is the difference between the outside and the inside. Okay, it doesn't do any good if you've got the same amount of sodium in as you have out. It's not going to go anywhere. It's not going to flow. That's why you maintain a strong sodium presence on the outside. So if you open a channel, it can come rushing in. The potential energy is how different it is from the inside and the outside. Think if you have a lake above a river and a hydroelectric plant. Now, if the lake is almost the same height as the river, you don't have much energy to turn that plant. But if it's really far above it, you can turn a big wheel and make a lot of electricity. So the bigger the difference between the outside and the inside of the cell, the more potential energy you have that you can use to set up an electrical flow if you really want to. And the way they designate that is the difference between the inside and the outside. Because the sodium-potassium pumps are pumping all that sodium out, it's a positive ion and you're getting rid of it, so you maintain a voltage inside that is much less than the outside. The voltage of the membrane is said to be negative 70 millivolts. That means it's 70 millivolts less on the inside than it is on the outside. It's a way of measuring the difference between the inside. If it's only minus 2 millivolts, there's no power to be had. But if it's minus 70, it's big enough that you can actually cause some things to happen. There's another force in play here, because we have our chemical forces, which are the concentration gradient. If I have a whole bunch of sodium outside and a little tiny bit inside, the sodium's going to want to come in by diffusion, right? Because everything wants to go from the high number to the low number in concentration. But then also, the sodium is going to be either attracted or repelled by the electrical charges, because positives repel and negative opposite charges attract. So if the inside of the cell is negative, it's trying to suck the sodium in. Okay? If you had so much sodium inside that the chemical concentration forces were pushing just as hard as the electrical was pulling in, you have what's called the equilibrium potential. You've reached a point where the electrical charges and the concentration gradient charges are equal, and if you open a channel, nothing moves. That's an important concept. I'm not going to force you to deal with it very much, but know what the equilibrium potential is. It's critical for passing AMP1 type courses and stuff. It's when your electro and chemical forces are equal and opposite so that they balance out each other and you have equilibrium. So our excitable cells, nerves and muscles are excitable cells. And because of largely the sodium-potassium pumps that are always pushing sodium out, now they're pushing potassium in, but not as much as they push sodium out. So you're losing more positive charges all the time than you're gaining, and therefore the inside of the cell becomes negative compared to the outside. And the basic number for that negativity inside an excitable cell is minus 70 millivolts. It's a good number to remember, because if it's minus 70 millivolts, that's normal. That's a resting membrane potential, and at that number, generally the cell is turned off. If you want to turn it on, you got to make it more positive. To turn it back off again, you make it negative again. Now, the cardiac cell is even more negative. So we'll see when we see how the ions flow there, they flow even with more vigor because there's a bigger potential. That lake is farther from the river, and therefore when you open that, they move really fast, and you'll kind of see what that looks like. But generally, you're keeping the cell really negative inside at rest. You maintain this negative 70 by, there's a certain amount of leak that happens. Some sodium's always leaking in, potassium's always leaking out. And then you make up the difference by the sodium-potassium pump pumping the sodium out and the potassium in. It pumps sodium out, which keeps most sodium on the outside, potassium in. So you have some leaking in both directions, and you have a lot of pumping in both directions. And what that does is maintain a resting membrane voltage of about minus 70 compared to the outside. If any of these get messed up, you get sick. Okay? Your cells will work too much or too little if that membrane voltage changes too much. Okay, and that brings us to the action potential. Action potential is basically when you create ion flows, electrical flows that turn a cell on and then back off again. That's what you're trying to do. If I want to curl my biceps, I've got to turn those muscles on and then I relax them again. I turn them on, I turn them off. I turn them on, I turn them off. So I have to have a way to do both. I have a way to stimulate those muscle cells by making the inside of the cell more positive, and then turn it off by making it more negative again. So we have a resting stage. You're about minus 70 millivolts, hanging out, waiting. Depolarization means you're going up because difference is polarized. Okay? If I'm getting closer to here, I'm depolarizing, depolarizing, depolarizing. Now I'm repolarizing to get it back down and turn it off. So a polarized cell has a difference between the inside and the outside. Depolarized, it's gone back up here close to the top, and then repolarized gets back again, and then you go back to your resting stage. To do this, we basically need to let sodium flow in when we want to make the membrane positive, because we're letting positive ions come into the cell, makes it more positive. And then we want potassium ions to flow out to make it more negative, because those are positive ions that are hanging out inside. Get rid of a bunch of them, you become more negative again. So sodium in, potassium out. Sodium in, potassium out. Turn the cell on, turn the cell off. Sodium in, potassium out. So the first thing you're going to do is, if you're at rest, you have to activate the cell, so we're going to need to let sodium come in. We have the sodium channels have three states they can be in. They're ready and cocked, but resting, which means they're not letting anything flow through. Okay? When they're activated, they open wide and let the sodium flow in and make your cell positive. Then when they get to the top, they have to turn themselves off. Otherwise, sodium would go in forever and you could never turn the cell back off again. And then they have to recock themselves so that they can work again the next time. So they're cocked and ready to go. They're shooting. They're reloading. And now they're cocking. Okay, so activated, they open and let sodium in. Inactive, they turn themselves off. And then they have to cock themselves to get ready to go again. That's kind of an important concept, because in some cases you'll have cells that will work, but then once they get turned off, you can't turn them back on again, and that cell becomes unusable. You can't get it to contract if it's a muscle. You know, it could be in some kinds of diseases where you're not able to reset those channels so they can work the next time. Here we have a cell that it's cocked, ready to go. All you got to do is open this gate and let sodium go through. You open it, the sodium goes through. Then you inactivate it by closing this other little lid, and now you got to recock it to get it back to the point where you can open it again, because you got to open this one, okay? But you close it with this one. That's not terribly important for you to know, except you do need to know that you turn the cell on by opening them. You stop letting sodium flow by turning it off, and then you actually have to reset it before you can use it again. That's kind of an important thing. Now, potassium channels are easier. When you're down in the negative range, they're closed. You get up pretty positive, they open. So the sodium channels open, and a whole bunch of sodium comes in. Now when you're getting positive, though, the potassium channels open. The sodium channels close, remember? And now the potassium channels are open, so they let the potassium flow back out. You turn the cell back off again. Then they close, because you're down here. So potassium channels are easier. They just open, close, open, close. Anytime a cell becomes positive, they open and let potassium out, so you get negative again, then they close again. And the phases of this action potential are usually demonstrated graphically. So you're going to want to be able to identify the different phases of the action potential on a graph and identify what kind of tissue it's happening in, because they look different. And the very difference of their shape will tell you what's going on. Phase 1 is when the sodium channels open and you depolarize. You become positive, turning the cell on. You usually overshoot past 0. You don't just go up from minus 70 to 0 and turn around. It's like skidding through a stop sign. You go a little past it, then you come back down to minus 70, and then you usually overshoot in that direction too, which actually helps you recock some of the channels that you need to recock. So phase 1, sodium's open. Phase 2, potassium's open. And then the sodium-potassium pumps work to push everything back where it's supposed to be so you can do it again. Here we go. Starting at minus 70. Here we have depolarization, sodium in. Repolarization, potassium out. A little hyperpolarization down here that helps you reset all those channels. And then you go back to minus 70 again. What's important on this graph is at about minus 55 is when all of these sodium channels open. So at rest, they're not going to open and make that cell fire inadvertently. You don't want your arm to do this when you don't want it to. You only want to do it when you turn it on. So we're going to stimulate this cell by making it positive enough. You can do it by turning it on with a nerve. You can turn it on with, a variety of different things. Some cells respond to heat. In your finger, you can feel temperature. Well, what you do is you cause the cell to reach this threshold point. My marker keeps going away. Reach this threshold point. When you reach there, all the sodium channels bang open. Sodium rushes into the cell, making it positive, and turns the cell on. Then the sodium channels turn off, the potassium channels open, and you come back down, you repolarize, and now you reset everything and put all the ions back on the side where they're supposed to be with the sodium-potassium pumps. Reaching this threshold is a big deal. If you don't quite reach the threshold, that muscle will never fire. Okay? But you don't want it to fire by accident, so that's why you have a threshold set up to make sure you give it a big enough signal that means I really want this cell to contract. And then it does. And then it resets and turns itself off. Sodium in, potassium out. Now, calcium plays a role during the action potential. First of all, in a muscle or nerve cell, calcium doesn't come in from the outside. It's stored in that smooth endoplasmic reticulum, right? Remember, we said that's one thing the endoplasmic reticulum does, is it stores calcium. And so when the cell gets positive enough, it causes a lot of calcium to be released from the endoplasmic reticulum, and it floods the cell, and that actually is what causes the contraction process to take place. So calcium is part of the contractile mechanism in muscle. In some kind of muscle, calcium does come in from the outside. In smooth muscle and cardiac muscle, which are different from arm muscle, which is skeletal muscle, smooth muscle and cardiac muscle, calcium actually plays a role in the influx from the outside that causes the cell to be stimulated too. That being said, let's look at the action potential in a couple of cells of the heart. The SA node and AV node secondarily, but the SA node acts this way. The SA node is your pacemaker of your heart. And so your heart needs to beat about once a second. And whether you stimulate it to or not, it's going to. It's sleep, you're not stimulating the heart to do anything. It's beating once a second on its own. The difference with the heart is that at rest, you have so many leaky sodium channels that it leaks and leaks and leaks and becomes more and more positive till it reaches that threshold on its own, and then it fires and resets and starts over. So you're constantly, see if I can get my hand here in the picture, okay? We're leaking sodium in, and then you reach the threshold, and a bunch of more sodium, but also calcium is a big player here. Calcium comes in, potassium goes out, and you redo it, okay? So we have sodium leaks in, calcium, potassium. Sodium leaks in, calcium, potassium. Sodium leaks in, calcium, potassium. All right? On a skeletal muscle or nerve, it's just sodium in, potassium out. Sodium in, potassium out. In the nodal tissue, though, the sodium brings you to the threshold by leaking, then calcium, potassium. Sodium, calcium, potassium. Here we go. Look. Sodium leaks in. Ignore this one down here. This shows permeabilities. Here, sodium is leaking in. You reach the threshold so that all those positive ions can come in and then go back out again to turn the cell on and back off. Sodium in, calcium, potassium. Sodium in, calcium, potassium. Sodium in, calcium, potassium. That's the SA node. And this slope here is the big deal. If I do something to increase the slope, my heart beats faster. See, it would happen sooner. If I flatten the slope, my heart slows down because I wouldn't reach the threshold till here. And it would take longer before the threshold was reached. So this slope of depolarization is called diastolic because that's the part of depolarization that happens between beats, is diastole in the heart. So your diastolic depolarization or slow depolarization is just the leaky sodium coming in, calcium, potassium. Now, the cardiac muscle cell has yet a third way of doing it. And it still has sodium, calcium, potassium, but they play a slightly different role. The depolarization, sodium comes in. In the middle, calcium comes in, but instead of making it go up further, it creates a plateau, which is important. It allows calcium to come in and help your heart beat stronger. And then repolarization, the potassium goes in. So here again, we have sodium in, calcium in, potassium out. Sodium in, calcium in, potassium out. So here's how it looks. Sodium in, it goes really fast because you've got a strong gradient. That -90 really pulls that sodium in, so you have a really strong influx of sodium. Here, this is a little resting phase here, which doesn't matter. Phase 2 is this plateau phase. If potassium were allowed to go out right away, you would just repolarize like a muscle cell does, skeletal muscle. But instead, you open calcium channels, and that influx coming in is influx. Influx of calcium keeps you positive for a little while, stretches this out, gives you more calcium to help the heart beat more strongly. And then, only then, the potassium channels turn on, and you have the efflux or outflux of potassium, which repolarizes, and you go back down to rest. Sodium in, calcium in, potassium out. Sodium in, calcium in, potassium out. This plateau phase is super important in the cardiac muscle cell because this is where you get enough calcium in to make your heart beat as hard as it's supposed to right then. We can control this. During exercise, we get more and our heart beats harder. Sodium in, calcium in, potassium out. And a concept known as the refractory period tells you how long after I stimulate a cell before I can stimulate it again. The refractory period is after I fire that thing, how long do I have to wait before I can get it to fire again? In skeletal muscle, you want it to be really fast because I want to be able to tetanize. I want to be able to hold my arm locked in place so those muscles are firing really fast. But in the heart, you never want your heart to tetanize and just squeeze. You would die. So instead, you beat, and that plateau phase stretches it out. Before you reset and can go again, that phase 2 is not only bringing calcium in so that you can beat stronger, but it's delaying the reset of the muscle so that you can't fire again quite as quickly. Here's a refractory period in a typical skeletal muscle or nerve or something like that. You have sodium in, potassium out. The refractory period basically is here. It's already firing. I can't get it to fire again. But when it's about halfway reset, I could get it to fire again if I stimulated it fast enough. Okay? So I could fire here and here and here and here and here. A short refractory period. In the cardiac muscle, let's go back to that one. From the time it fires, I couldn't get it to fire again now. I couldn't get it to fire again now. Nothing's reset yet. I have to be good, halfway down here before I could get my heart to beat again. And that's good. You got to wait a little while before the next beat happens so your heart doesn't just tetanize and cause you to die. Longer refractory period. And generally speaking, anything you do that makes the membrane more positive brings you close to the threshold and makes that cell easier and easier to fire until it finally does. So if something happens, either good or bad, that brings it too close to the threshold, you're making it more and more easy to fire. If something pushes the membrane more negative, so you're farther from the threshold, I can't get my hands here, farther from the threshold, you've got so far to go before you can get it to fire, that it inhibits the cell. And that in our brain and various places, we have all kinds of inhibitors that hyperpolarize those cells and make them more difficult to fire. So you don't have seizures. You're not having them fire all the time. So anything that will depolarize the membrane, make it more positive, makes it more likely for it to fire. Anything that hyperpolarizes the membrane, makes it farther down, means it's going to be less likely to fire, and that cell is inhibited. So, how are we going to take a cell that's at minus 70 and push it up to minus 55 or so you reach the threshold and the thing fires? You have to generate a potential change somehow that pushes it up high enough that then all of those automatically activated channels open, the sodium rushes in and the potassium rushes out, and that cell actually fires. So a lot of things can generate this action potential. Pressure, if I just push my finger against something, I have pressure receptors in there that open enough channels that those cells reach their threshold and fire, and I can feel the pressure on my finger. Temperature, I can feel hot and cold. Signal from another neuron. If there's a nerve that stimulates my membrane to the point where it lets in just enough sodium to cause it to reach the threshold, it will fire. Sight and sound are called evoked potentials. Light shining on your retina activates specific cells that respond to light, and it opens just enough channels that they reach the threshold and they fire, and you see stuff. Same with sound. Chemical stimulation. You can bind molecules, hormones, or you can even bind something to your taste bud. It opens enough channels to cause you to reach the threshold, and then you fire and you taste something. The transduction is what it means when you take pressure and convert it into an electrical signal. I'm transducing the heat from the air into an electrical signal that I can interpret as heat. So now we're going to take that signal and send it to somebody else. Remember, the whole point of this was so that you can signal a cell to turn on. I can signal my heart to beat faster. I can signal my respiration to increase. I can signal my temperature to go up. I can signal my legs to run. So what I have out here are all these sensors. They sense pressure, they sense temperature, they sense, whatever, they are designed to interpret as a signal. Enough channels are open there to let sodium start flowing down in here, flow down in here, flow down in here. If enough positive charges reach here, it opens the channels and causes a bunch of sodium to flow in. And that signal, that sodium flowing in, is an electrical current. It is transduced or taken all the way down this axon. Then it goes out into the axon terminals, and each one of these can turn on another cell. So if I get a signal from my brain that says I want to move my arm, enough sodium comes in here, opens enough channels to cause the signal to go down here. It goes out of here and it stimulates all of these leg muscle cells, and my leg contracts. These are the dendrites. They receive information. The cell body is the cell itself, or the nucleus, but it also has the area where it can then open and send a signal. So the cell itself determines whether the signal is big enough to be worth sending. The axon takes the signal all the way to the far end. These cells can be, some of them can be 3 feet long. They're microscopic, but they can take a signal from your brain to your leg. And then the axon terminals actually take the signal to the individual cells that need to be turned on. Okay, again, this is a repeat. Here we reach the threshold. The axon at that proximal end needs to open and let sodium in. Then it closes, potassium goes out, and you start over. So it's an excitable cell, just like any other excitable cell. It will have the same kind of action potential of a current flowing in and a current flowing back out again. These electrical signals, turn it on and turn it off. You can get enough signal into that cell body to make it turn on by a couple of ways. It's called spatial or temporal summation. Look at this. If I have a little bit of signal coming in from all over the place here, I can get enough ions in here to finally reach the point where I'll turn this on and send the signal. Or I can have a ton of signals coming in from one. You know, that's temporal. Coming in really fast. Temporal means time. I can get enough sodium from this one guy to turn it on. So I describe this spatial summation as like a sunburn that's over your whole back. It hurts not super bad, but you know, there's so much of it, it makes your back hurt. But temporal summation is like sitting on a nail, sitting on a thumbtack. You get a ton of signals from one area, and that would be enough to get your cell to fire and say, ouch. So here we have all the signals coming in. They reach here, where you have all of these sodium channels ready to open. You know, if you can reach the threshold there, those sodium channels will open. Sodium rushes in. Now it's positive inside the cell, and therefore it turns on. See, this is the way it was, positive outside, negative inside, negative 70. But when the sodium rushes in, it becomes positive in here, and that turns this on. Now, those positive ions don't just sit there. They kind of diffuse away from that site, and this becomes positive enough. It reaches the threshold, and these guys come in. And they flow down here, and they reach the threshold here, and these guys come in, and these guys come in, and these guys come in. And that's the way you propagate or send that signal all the way down. Every time positive ions go here and reach a threshold, more come in, more come in, more come in. It's like running down a hallway and throwing open the doors, and more people join you all the way down to the other end. So you always have fresh people running. So you keep that signal going nice and fast all the way to the far end, because it's always fresh concentrations of people or ions all the way to the far end. So from the trigger zone at that proximal axon, it goes down to the far end basically with no loss of strength, because you're constantly getting more ions coming in at every step along the way. See, now here's move from there to there. Now it'll move from there to there. Now it'll move from there to there, and there to there, and there to there, and there to there, and there to there. On the outside, you see, as this flows this way, the outside ions flow that way. So if you're measuring it from the outside, it'll actually look like the ions are flowing from this way to that way, when they're the ones that matter are going that way. The signal is going that way. It's just the backflow here that backflows to fill the gap that's going the other way. So if you're doing an EKG machine or something, you have to reverse it automatically reverses it for you and shows you that these ions are flowing in that direction. And those are the ones you care about. So, that's a good way to get a signal to go somewhere. It's not especially fast, because the ions have to come in, and then they come in here, and then they come in here, and 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 they come in here. And it'll make it moves about half a meter a second, 1001. Well, that's okay. But if I step on a nail and my foot is almost 6 feet away from my brain, I don't want to have to wait 12 seconds before I discover that I've stepped on a nail. It's got to go faster than that. So our body achieves really fast transmission of signals by what's called myelination. Myelination of the fiber. You take a cell that wraps around it, and it prevents ions from going in and out here and here and here. They can only come in and out here and here, and here and here, and here and here. These are called the nodes of Ranvier. The nodes of Ranvier. That's where it actually happens. And so when the ions come in here, they just shoot down there and cause it to happen here. And it shoots there and shoots there and shoots there and shoots there. It's like the difference between if I grabbed a softball and I had a mile-long tunnel, I could just grab it and try to run to the other end of the tunnel. Or I could have somebody spaced 50 feet apart all the way down there and just whip it down to the next person. Throw, 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 throw. It would go so much faster that way if the people were any good at softball. And so it makes it go like 50 meters per second. I mean, it's really fast, It goes really fast. So you step on a nail, and you stepped on a nail before you even finish putting all your weight down, because the signal makes it to your brain so fast. A couple of kinds of cells cause myelination. In the peripheral nervous system, in your arms and legs, you have these Schwann cells. A Schwann cell that wraps around like a stick of juicy fruit gum to prevent the ions from flowing in and out here. And you have another Schwann cell and another one. Here in the central nervous system, you have things called oligodendrocytes, and they look like little octopuses with legs. Each one of them has a juicy fruit on the end. But what they accomplish is the same thing. They're creating this node of Ranvier thing, so the signal jumps from here to here to here to here and goes much faster. This is critically important because demyelinating diseases like multiple sclerosis or, there's a couple of them, muscular dystrophy, demyelinate, and the signal slows down or even stops before it can get to the far end because it's not designed to have to deal with moving here and here and here and here. The channels aren't proper there, and as the demyelination gets worse and worse, you'll get so you can't even move that arm or leg. So a demyelinating disease or toxin or something is a real serious neurological problem. Here we have the myelin sheath with the Schwann cell. And here we have the node of Ranvier, where there's no Schwann cell, where the ions can go in and out here. So the myelin sheath makes it go really fast as 100 meters per second. That's the whole length of a football field in 1 second, as opposed to half a meter per second. You may see the term saltatory conduction. That just means jumping. Saltatory conduction happens in myelinated nerves. That's it. It's that jumping signal. And the signal happens the same way. It jumps from here to here, then it kind of backfills. But then it jumps from here to here, jumps from here to here, jumps from here to here, all the way down to the far end, where then it can signal the cell at the other end. So we got to try to make this work. Look. See, there's a non-myelinated fiber. See how slow that is? And look how fast this is. Ta-da! Demyelinization. Once again, the signal dies out too fast before it gets far enough to do its job. It dies out because it should be going before it has a chance to lose any power at all. Instead, it's dying below a threshold level before it gets to the far end. Some basic layout of the nerves and nervous system. We'll be more specific on these when we get to the muscles and nerve parts of this course. I do this early on. I don't wait for the nervous system part because we have to turn on the muscles and even the bones to some degree, and you have to be able to use the nervous system and hormones to do it. So I give you the turn on part now, and then by the time you get to the nervous system, we're mostly talking about anatomy, where they are and what they do. So types of neurons, they come in small, medium, and large. Large myelinated neurons take the signal really, really fast. Small, unmyelinated take really, really slow. You have A's, B's, and C's. The A's are the fast, the C's are the slow. C's are unmyelinated. They're the slowest ones you have. They're usually really short. They don't have to go very far, so it doesn't matter that they're kind of slow. But they also could be for slow pain. You know, if you have a pain in your stomach, you don't need to know it within a hundredth of a second. You know, a half a second later is good enough. Whereas in your leg, you're going to have the big A. And the fastest of the A ones are called A alphas. These are the ones you need to know right now because A alphas are used in the skeletal muscle. You want your arms and legs to get signaled right now. So you use the biggest, fastest. Alpha motor neurons. Alpha, like alpha gorilla. The A alpha motor neurons are the biggest, fastest ones. We will see later an A gamma motor neuron that works in the muscles for sensory positioning in space and that kind of stuff. They're still big and myelinated, but they're not nearly as big as the alpha guys. So mainly for this first test, remember that A alpha motor neurons are the ones that run your skeletal muscles. And finally, the most basic overview of just how our nervous system is laid out. So when we're talking about, okay, what's going to turn on the muscles and what's going to turn on the stomach, okay, but what's going to turn on the muscles? The somatic nervous system is your voluntary nervous system that runs skeletal muscle. Soma means your body. This moves your body. The somatic nervous system, skeletal muscle, alpha, A alpha neurons. The autonomic nervous system runs things like your heart and your stomach and your GI tract and your liver and whatever else, things. Controls your blood pressure, causes your blood vessels to squeeze or relax. The autonomic nervous system is divided into the sympathetic fight or flight half and the parasympathetic rest and digest part. Somatic nervous system, for this good part of this course, we're going to be dealing with the somatic nervous system. You will learn about the autonomic nervous system as we get more deeply into the course. Right now, somatic, skeletal muscle, alpha motor neurons. I told you that was a ton of stuff. It's a lot of different concepts. Go back through it, look at the things that are highlighted in red. Look at your practice questions. The take-homes that I really want you to know the most are represented by questions in the practice questions. So before you start reading a ton of stuff, go through there and it'll help you focus your studying. And then also, we're going to do a lot in the labs, the lab manuals, the top hat, stuff, that's going to really start bringing some of this stuff to light as well. All the best to everybody.